So for this lecture, I'll talk about the differential form of the Maxwell equation. So before we need to know how does the differential form of the Maxwell equation come from, we need to have some math so that we can derive it out. It is known as the Divergence Theorem or the Gauss Theorem. The other one is the Stokes Theorem, which is the three dimension of the Green's theorem. I'm not sure whether you have learned it in math class. Have you learned it in the math? Stokes theorem and Gauss theorem, Stokes theorem and Gauss theorem, also Green theorem. Have you learned that? No. No. What did you learn in the math class? Okay. Oh, and finally, I'll talk about the conservation of charge, which is related to the Maxwell equation, and most importantly in the Ampere's law. So, as we have learned in different chapters, for example, Gauss Law, we learned it in chapter 23, Ampere's Law in chapter 29, Faraday's Law in chapter 30, and Gauss Law or magnetism in really this chapter. But actually, these two are very similar, and actually this is quite simple because something is equal to 0 is very good. So far we know that for E field and B field, we know that, for example, for the first one, if we need to calculate the net flux of the electric field, that will be equals to the charge enclosed by this area, by this volume, or by this surface. And we know that we don't have a magnetic monopole, so that a closed surface encloses the net, something like the magnetic charge, or it should be known as the magnetic dipole, should be 0, because for a magnetic dipole, which means that it has both north pole and south pole, so that you also the north and south will always cancel each other. And the Faraday's law and Ampere's law are another pair of laws. So this one is telling you that when there are magnetic flux changing, it will generate and induce EMF, and it can be written as a line integral of the electric field. Likewise, the Ampere's law is something like if you have a current or changing E field over a area, or both of them, then you have that it will generate the magnetic B field, the magnetic field. So this is more or less implied in the integral form of Maxwell equation. So we can rewrite these two like this, which is nothing special. The magnetic flux is nothing but the surface integral of the magnetic field over an area, and this is the line integral, so that we use ds, and here this is dA. So this is dA, they are surface integral, and likewise for phi b, it is the electric flux, so we can rewrite it as a surface integral of the E field. And this is the notation in the textbook, so we'll make it more specifically. because when you see all of them are integral, and these two may look similar. That as long as you don't know what is CS and what is CA, because different textbook may have different notation, so it's not really good in my opinion. So we could rewrite them in like this. So for the Gauss law, it is a surface integral, so that we use two integral sign to specify it is a surface integral. And actually, on the right side, the Q enclosed can be written as a triple integral. So we integral the the charge density, the charge volume density. We integrate the charge volume density over a volume, so that this is the total charge in the volume. It's something like you multiply the density times the volume, then it is the weight, something like that. When you consider it is constant over the area, but here the density is not necessarily constant, so we use a triple integral generally. So for the magnetic version, it is 0, so that we don't need to change it. And well, here for Faraday's law on the left side, it is a line integral, so that we still keep it as a single integral, and this is a double integral. And for Ampere's law, originally this is mu 0 I. I is something like static current, or it may be time varying, but it is really a current. And we can rewrite it as the surface integral of the current density. So I think it is already defined in chapter 26. If I remember something right, we should have defined this, but here we try to make all the terms are something like single integral, double integral, and triple integral, and so on. Only these three types. So we have the Gauss, the Maxwell equation can be written like this form. So up to now, is there any questions? Okay, 待会你就知道。This is some preparation work. So for the next few slides. But so I try to write it here to make you get used to it, and then a few page later, then you know, this is really like this. Okay, so we jump to the answer first. The differential form of the Maxwell equation will look like this. So you have the divergence of E will be equals to the charge density over the epsilon 0. And for magnetic version, it is divergence of B field equals to 0. And for Faraday's law, is the curl of E equals to minus partial B partial T. And Ampere's law will something look like the curl of B equals to mu J plus epsilon 0 partial E partial T. So we need to see this variable. Then we can try to remove all the integral side. Then we'll see something like this. But there is something changed on the left side, you see something like a triangle with a dot, triangle with a cross, something like that. So this is the differential form. Huh? Gradient. If it is only a gradient, then it is gradient. But if it is a dot here, it is called a divergence, and this is called a curl. This specify how many flux in the space, and this one specify how the E is rotating. So in summary, it will look like this. This is the integral form and the corresponding differential form. So let's jump to the next page, which is about the divergence. So divergence can be seen like this. You know that the gradient operator in chapter 24. You learn that E equals minus gradient V. That's what I let you know in chapter 24. So V is a scalar field, and E is of course a vector field. This is the E field, and gradient is something like an operator. So we can write the gradient to be like this in Cartesian coordination. If it is in other coordination, it will look more complicated. But in Cartesian coordinate, it will be something like this. The unit vector in x direction, and then you take the partial derivative with respect to x, and then for y direction times the unit vector in y direction and the z direction, and the unit vector in z direction. So gradient operator is something like this, and if you have a scalar which is operated by this operator, then you can calculate it with, for example, V. You can take the derivative, because V may be a function of x, y, z, so that you can really take the partial derivative with respect to x, y, or z. So that if we have the full knowledge of the electric potential in the space, then you take the gradient and multiply by -1, then you know the E view in the space. So divergence is a little bit different. There's an inner product followed by the gradient. So and actually we call it the divergence. So if you have a vector field, namely F, or it can be E field, B field, or other field. But if you have a vector field F, and then it can be written as Fx times which means x direction of the F, y direction of the F, z direction of the F, so that we separate into different components. We decompose it in different components. So we can decompose it. IGK are three orthogonal bases. If you consider in a linear algebra point of view, there are three independent bases, so that we can project F in these three directions. And the calculation of divergence can be written like this. So we take the x derivative, partial derivative of with respect to x for fx, take the partial fy, partial y, partial fz, partial z, then this is the divergence. Because you can also consider it as an inner product. So this one is vector, this one is also vector, and then the answer should be a scalar. So you can consider this term inner product with this one, so that only the partial x, fx is remain. But if you have this term with the right component, then I dot j is 0, so that this one does not exist. So only 3 terms will exist, because originally, if you write it like partial c I plus partial y j plus partial z k and fx I plus fy j plus fz k. So if you multiply it out, then you'll get 9 terms, but 6 of them are zeros, and only 3 terms are remaining. So the only 3 terms remain are partial x, fx, partial fy, partial y, partial fz, partial z. So this is the definition of divergence. Any question up to now? So it is so far very easy. So the physical meaning for divergence is something like if divergence of f is larger than 0, then the f near that point would be pointing outward. Oppositely, if divergence of f is less than 0, you see the f tends to pointing inward. Maybe some are pointing outward and some of them are pointing inward, but the overall to this point will be negative, which means there are more pointing inward than pointing outward, or maybe all of them are pointing inward. For if it has divergence of f is equal to 0, you don't find any inflow or outflow, so it will something look like something like this, or not really like this, or maybe all of them are pointing to the same direction, so that if you just circle some point, then you see this is going in, going out, going out, going in, then the net flux is 0. But actually, after taking the divergence, this is also a field, a scalar field, so that if you substitute the XYZ into this expression, then you know the flux at different points over the space. This is what I just mentioned. This one is also a field, so it will still be a function of x, y, z, or maybe it is a constant, but actually this one would still be a function of x, y, z. So that when you want to know the divergence at this point, you substitute the coordinate of that point into that expression, and you know the flux at this point. But actually, it tells you all the flux over different spaces, over the whole spaces. 不用积分了，不用积分。我们不会积分，我们不会积分。Integral is not very friendly. You can only do it in exam, but actually when you compare it in computer, will not use the integral form. Integral form is not convenient to use because it depends on the symmetrical different kind of symmetric, spherical symmetric or plane symmetric, something like that. When you learn in chapter 22 and chapter 23, you know that as long as you have some types of symmetric, then you can cancel something to make the calculation more simple. But actually, it's not really useful practically. So we feel like using the differential form because it is a PDE. We can solve it using the finite element, something like that. And actually, I think the EM simulator will base on the differential form of the Maxwell equation, because the integral form you already calculate the E field over a surface, but actually for general case it will not be uniform, so that you don't know all. You only know A plus B equals to 10, but you don't know what is B. That's the problem. But here, it's specified for a certain point. Then you know the difference between this point and its neighbor, so that you can use the finite element to find the field over the space. Okay, and the next one is the curl. Curl is a little bit more complicated. We have similar definition for f, which is fxi plus fyj plus fck. And actually, curl is a cross product between the gradient and the vector field. So we can use the definition of the cross product. Then you can write it in the determinant form like this. So you have the first row ijk, the second row partial x, partial y, partial z, and the third row is fx, fy, fz. So finally, you can expand the determinant so that if the curl of y can be written like this, I is partial fz, partial y, partial fy minus partial z, and so on. For this, you only need to expand it. Then you get this expression, and this is the definition of curl. Definition of curl. It's more or less like you have this one, and this one. This is positive. This one, this is positive. This one, and this one positive. This one negative. This one negative. This one negative. So you have totally 6 terms. So this is an example field for the curl. So for example, if you have a vector field f like y times I minus x times j, then you can calculate that the curl of f is minus 2k. Which means that over the space it is rotating clockwise. If it is counterclockwise, it is positive. And k means it is rotating like this, so it is pointing inside, following the right hand. So calculating this is very simple. You just need to substitute into here, then you get this expression. You know that this vector field is rotating clockwise along the z-axis. Because this is x direction, right direction. So use the right hand rule. Z direction is outside the board, and it is rotating clockwise. So it is inside the board. So it is there's a negative sign. So this is a visual demonstration for the curl. This one tells you how it rotates. This one curl tells you how it rotates, and the divergence how it the flux, whether it's falling out or falling in. And this one tells you whether the field is rotating. If you need to see the original definition for the field, it is yi and xj. So that this is what you mentioned. Actually, like that. And you know at this point, it is x is for example this point x is minus 2, y is 2, so that pointing to this direction. But if you calculate the curl of f, then it is minus 2, which means that it is over the space. It is constantly rotating in clockwise over the z direction because it is k. You haven't learned that? Gradient.如果归一点是啊，但是这个是看它怎么旋转。Because when you learn the magnetic field starting from chapter 28, you use a lot of cross product, and cross product is just like A cross B, then the answer should be perpendicular to both of the input. And it will tell you how the stuff is rotating. And you know, when you learn the Lorentz force, you have circular motion of the particle, something like that. Or actually, they are all rotating. And for example, if you have a current in a straight wire, then the B field tends to rotating around the wire also. So that's why I say magnetic field is more difficult, much more difficult than the electric field. Electric field is feel like easier to understand, but as long as magnetic field has so many relate to the cross product, then you need a lot the right hand rule, and then then the mind will also blending. So is there any questions? If no, we'll go to the next stage, which is about the divergence theorem. So last lecture you asked a very good question, because the Maxwell equations try to relate the single integral with the double integral, and also the double integral with the triple integral. But how it related, it is mostly about these two theorems. One is the divergence theorem, another one is the Stokes theorem. I'll not show the proof of these two theorems here because it is very lengthy. You can check it in this link. It's something like seven pages of math to prove these two theorems. But I just here to tell you what is the physical meaning of these two theorems. So for the divergence theorem, it tries to link between a surface integral with a triple integral. And for the left side, this is actually the flux. You more or less similar to it because the Gauss Law. Then we change F into E, then it is the left-hand side of the Gauss Law. And for the right side, it is the triple integral, which means that it is the volume integral. The volume is enclosed by this surface on the left-hand side. But we need to have some trick between them. We need to take the divergence of F, and then we take the triple integral, so that it will be equal to the original flux. So it is how it try to link the double integral to the triple integral. And the physical meaning of that is something like, I try to draw it, something like this. Suppose you have a volume. I cannot draw 3D, so I compress it to 3D, but I hope you can understand. But as you know, divergence of F is something like to tell you how is the flux of a point. So we have divergence here, something like this. For the neighborhood point, we also have the divergence, something like that. Something like that. And for here, we also have the divergence, something like this. So over the whole volume, we can calculate the divergence. We can calculate the divergence. And actually, for the inside part, for example, this one and this one will be cancelled with each other. So that finally, the only flux that can contribute is only the surface. And all the inside of the flux will cancel with each other because they have neighbor point. And at this point, we'll have something like this. So this one and this one will cancel with each other. Then finally, only the surface part will remain. That's why we can calculate the divergence of F, and then we integrate over this volume, and finally, the inside part are cancelled with each other. The only terms remain are the surface integral. That's the physical meaning of the divergence theorem, or known as the Gauss theorem. So this theorem is very interesting to link the triple integral with the double integral. So this is triple integral, but you need the divergence, the right divergence operator. So for the Stokes theorem, it is quite similar. I can say they are something like brothers. It tried to link a line integral with a double integral. So Stokes theorem tells you that the line integral of a vector field over the boundary of a surface equals to the surface integral of the curl of the vector field over that surface. So actually, you have a line integral, something like this, and you calculate a surface integral which is bounded by this contour, and then the only stuff you need is the curl operator. You calculate the curl operator, then this one is equal to this one. So as I mentioned, curl is something tells you of whether it is rotating. So the physical meaning for this is something like you try to calculate the line integral, for example, over this contour, and you have the curl. Originally, you want to calculate the the line integral. The line integral. We want to calculate the line integral, but it will be equivalent to this. It is actually a double integral, but you calculate the curl of f over the surface. Over the surface. The surface is bounded by this S. And as you know, curl F is something like how the field is rotating. 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 And then you integral this stuff over the whole area, then you'll find that actually this one will cancel with this one, which means that the inside part will also cancel each other. So you calculate all the curl over the whole area. Calculate the curl, and this curl will cancel with all this part. So finally, only the outer, the surface, the outer part will remain, and this is actually the line integral. So you can calculate the curl of the field, and then you integrate over the surface, and then you equal to the line integral of the boundary. So it is more or less what the Stokes theorem mentioned. Actually, it is the 3D version of Green's theorem. Green H. 3D version of So this is actually the 3D version of Green's theorem. Green's theorem is in a 2D version. So originally we have the Gauss Law, something like that. Gauss Law, like this, which is what you're familiar with. And we can rewrite it, rewrite the Q enclosed as a triple integral. And according to the divergence theorem, the next flux can be written as another triple integral. But we need to take the divergence of the E field so that we have a divergence theorem like this. And we substitute this into here. So that we'll have the triple integral of divergence of E equals to, we substitute, we put the epsilon 0 inside so that we have the triple integral of rho over epsilon 0. And this is over any volume over the space. So the argument can be something like, because this volume is arbitrary, so that every point should be the same to make the whole integral to be equal to each other. So that the inside part should be equal to each other. Or you can consider V to be a very small sphere, and then you let the V tends to 0 to be a very, very small sphere, so that it is something like a very small dV, which is constant. So this term will be constant in a very small volume. Then this part should be equal to this part. So we have the differential form of the Gauss law. And similarly, we have the magnetic version. Divergence of E equals to 0. So we have these two equations for the Maxwell equation as the differential form. Any questions? So let's have a 15 minutes break.